All right. Well, welcome back from lunch, everybody. Now that they've turned the lights down and we've had lunch, so hopefully nobody takes a nap. But if you do, I won't judge you. Um, I'm Tyler Lamb. I work with Allsteel on our development team, working with CET, and I'm going to talk today about the adventures I had implementing electrical, mainly in our panel systems, to give you guys kind of an idea of some of the challenges we faced, kind of tools we used to solve the problem, and then hopefully help anybody else out that needs to tackle that endeavor if it ever comes to it. So, first thing we're going to talk about are graphs. So I'm going to be hitting you guys with stuff about like GDOTs, GREX, things like that. Beginner development course. Oh, sorry, Paul, that's your thing. Uh, so let's move forward here. See if this clicker works. Clicker does not work. Sweet. Oh, there we go. So first, talking about a graph. I want to kind of just level set some of the terminology. Apparently the screen is very much cut off, so that's awesome. So graph is basically, you think about, like, if you want to think, the easiest way to think about it is if you're thinking of a map. So you've got a map of, a couple cities and how those cities connect to each other with some roads. So if you guys ever come and visit Iowa, these are basically like the main, like 6 cities you need to care about. So just an FYI. So the cities in a graph would be represented by nodes, basically. So we've got different cities for like Iowa City, Quad Cities, Muscatine, Cedar Rapids. Those would be the nodes. And then to be able to travel between those, the roads kind of would represent the vertices. So if you bring in the roads, those are referred to the not the vertices, the edges of the graph. So the edges connect the vertices to each other. So it talks about how you can get from one place to another. So to go from Cedar Rapids to Des Moines, you can't get there straight. You have to go through another node to get there. And then given the different kinds, there's also a bunch of different kinds of graphs. So there's directed versus undirected. So a directed graph is like what it's showing right here, where it tells you which way you can go down between nodes. So right now I can go from Des Moines to Iowa City, and I can go from Iowa City to Des Moines. You may have a directed graph where maybe you can go from Des Moines to Iowa City, but you can't go back the other direction in the graph. And then usually a undirected graph, you just kind of think of doesn't have the arrows, so you can go either way. So that's kind of representation of that. And also a graph, the edges might have weights, and we refer to that as a weighted graph. So then that tells you, how difficult or the cost to traverse that edge would be. So to go from Ames to Des Moines, it's 15 miles. It's not really, but just FYI. So that just give more information for your code to make proper decisions about traversing this graph. And then we also talk about there's cyclic and acyclic graphs. So a cyclic graph would mean that you could basically kind of keep going in a circle in the graph kind of infinitely, whereas an acyclic is not. So this kind of shows what like an acyclic graph might look like that is not a complete cycle. And then connected versus disconnected. So connected graph means that every node is connected to another node in the graph. There's no breaks in the graph to have like 2 separate subgraphs. So any questions on that? So we kind of I know it's probably a review from a lot of you from college courses, but it's kind of one of the level sets people kind of understand all these terms so that they make sense. So the first thing I'm going to do is look at the implementations of the graph. There's 2 ways you can implement it. And I just want to show this is kind of the example graph I'm going to use. We just have a very basic graph that just has 5 nodes, and then they're interconnected certain ways. So the first way you can implement a graph in code is called an adjacency matrix. And so basically inside your code, you will have literally like a 2D matrix that you will use to store. You'll have reference to each node across both dimensions of your matrix. And then the value of those, the values in your matrix will represent the cost to go between those edges. So for example here, if you're going to go from node 1 to node 2, the cost is 1. As we can see, oh geez, I shouldn't have clicked that apparently. Let's try that again. Present. All right, I'm here to talk about graphs now. Funny animations. I got to play through all these again. Okay, so don't use laser pointer. Got it. So we can see that if you wanted to go from edge 1 or node 1 to node 2, it's going to cost 1. Whatever you decide that weight could be. So like in the map example, I used miles. In your code, it might be, maybe a cost, like a physical cost, like, oh, it's $5 for this part, so we would do that type of thing. And so the perks of this is that it's really easy to see what's connected to what very quickly. I mean, if you remember from programming classes, again, you got like the big O notation. I mean, so accessing to see if there's a node or an edge connecting two nodes is basically constant time. So it's pretty easy to do that. But then the problem is that if you need to go over everything, it's kind of heavy to use that. So use the mouse here. Let's see if that helps. And then, so basically here, I just whipped together really quickly just a sample implementation of an adjacency matrix in CM code. So you can see here, we've got the matrix as a private variable, then the size. So when you can instantiate it, it instantiates the matrix. And we just have some simple sets, gets, check to see if node is valid, things like that. And then some sample code just filling that and then just kind of showing the sample output, just to kind of give you guys an idea of how that might be implemented in CM code. The other way that you can implement a matrix, another way you can implement a graph is called an adjacency list. So it's somewhat similar to the matrix, but you kind of think of it more as like a linked list type implementation. The nodes know what nodes they're connected to, and so you basically kind of have this simple kind of road that you can travel down. So I can see that node 0 is connected to node 1, node 2, and node 3. And so, and with those connections, you usually carry the cost as well. So like there, I'm just saying that the weight is noted in the parentheses. So to go from 0 to 1, it costs 2. If I want to go from 0 to 2, it costs 2. Things like that. So with these, the challenge is that it's more difficult to know if an edge exists because you got to iterate through the list a little bit more to be able to see if the edge exists. And then chances are you're probably going to use less memory storing it this way. So that's usually a perk if you need that, but you kind of got to think about what your needs are from your graph to decide how you're going to implement them. So, and this is just a pretty simple implementation of an adjacency list here again. So the same thing, we got a private member variable to hold the list. Constructor doesn't really do anything, and then basically add node and then the add edge method. In this specific implementation, I'm doing this as a undirected graph. So when you add the edge, you're actually seeing that I'm adding the edge to both the source node and the destination node. So that way they both are connected to each other. If you were to do a directed graph, you tweak your implementation there. And then again, just some helper classes I've got over there, and then a simple method where I populated that graph that I showed a couple slides ago, just kind of showing what the output of that would look like, just to give visual representation. So that's about all I got to say about graphs and the implementations of those. Give you just a quick overview again of what those were. So now I'm going to talk about really what you got to do to solve electrical in your product. And may be helpful, may not be helpful. It just depends on your product, to be completely honest. Because I found with every product that we've done it in, it's always a new set of challenges that we've got to tackle. So there's never like a one hammer fits all for this for a solution. But I feel that having the information can be very helpful to making the decisions you need to make on how to solve these problems. So kind of the first thing you got to worry about is how are you going to place the components that they need to place. So things like, outlets, jumpers, data ports, things like that. You got to think about how are they going to place those in your your products. So how you do that, you may use animations, quick properties. It really depends on your product. If you got something that's very, there's a lot of configurations they can do, you probably want to use an animation to place those so the user can place them where they want. If there's like a single place it can go, maybe it would make more sense to just have a quick property to turn electrical, outlet on, off, things like that. Then you're also going to need a way to store that information on your snapper so that way you can obviously, when they save a drawing, open it back up, copy a snapper, those things go with it. So just things to keep in mind. These are all problems that we kind of faced when we were implementing this. And the thing that the mantra we went with is you want to give the designer as little work as possible. They're not going to want to be placing parts that are internal electrical components most of the time. They're probably not going to want to place, oh, I need a jumper to go through all of this. These other internal parts that are just things that should be placed that are kind of automatically based on, by knowing what they want to do, you should be able to place some of the parts for them potentially. And again, that may vary from product to product, but those are things to keep in mind. Give them as little work as possible so they can focus on doing what they need to do. And this is a picture that I took from our headquarters, just to show, they put this together in our training room just to show how ridiculous the electrical can be in some of our panel systems. So this one panel system, I believe it can have outlets like every like 10.5 inches. So just it, I saw this and I was like, oh crap, this is what I got myself into when I just signed up for this project. But the main thing is you got to take the time to understand how electrical works in your product, because you're going to be dealing with a lot of the nitty gritty, and there's not going to be potentially, like the problem I had is there's not a lot of people that know a lot of that nitty gritty stuff about your product and how things work exactly. You've got to find the right engineer on the right day to talk to see how that works. So really, you need to have a very intimate knowledge of how the electrical is routed in your product, how it's spec'd. So you got to talk to designers, your engineers, your training team, what have you. And that's, I can't stress that point enough, really, because it comes down to, there's times now where I'll get bugs submitted through our extension. They're like, this isn't right. And then I look at it and like, no, that is right. That's how it has to route. You can't route it that way. It doesn't work. So you kind of have to be able to defend your code then too by having this product knowledge. So I just wanted to make sure I stressed that point. So really now we're going to take talking about, okay, so now we've got a solution to put the product, or put the electrical components in your product. And I apologize if I say panels instead of product. It's just because that's what I'm using for an example here. So this is a screenshot of our extension. So I've just got simple panel layout. So basically we need a way to connect these things together in code. So if we go ahead and say, okay, these things connect, which I've actually got some of these parts here just to kind of show for an example here. I just thought I'd bring these. But so basically we've got these parts go in the panels. So this is analogous to this piece right here. So basically their connections are on the outside for how these things actually connect to each other. So if we go ahead and drop, I just drew some yellow circles on where these things to connect to each other. We need to have a way to actually connect these together. So we could probably just take some lines, connect them together, be good, right? But the question is, how do we do that in code? So we think about, there's lots of ways that these can be connected together, right? So that's going to be a problem, because that'd probably be a lot of parts to order. The designer would probably not be too happy if they got that. So what we need to do is a way to figure out, okay, well, what's the best way to hook these things together? So we've got a lot of options. Let's see. I'm sure there's probably some sort of algorithm that some smart guy came up with at some point in computer science that might be able to help us. So there's this beautiful thing called the minimum spanning tree. And it takes a graph, and then you can essentially give it where you know where your nodes are and the edges, and you can give it all the information. Then it'll basically spit out what's the shortest or cheapest way to connect all those nodes together. And it's, again, here it's used for a connected, edge-weighted, undirected graph. And then, like I said, it gives you the cheapest way to hook all those things together. So if we click and nothing happens. So that talks about a minimum spanning tree, but the problem is, how do you actually do that to build that minimum spanning tree? And there's an algorithm called Prim's algorithm, which is pretty good at doing this. And so you can see this GIF that I have on here. Basically shows what it does, but basically you can start from anywhere in the tree, or graph, sorry. And then you basically look at all the edges that are connected to that, and then you just always take the cheapest edge from that point. And then once you go to the next node, you add all of its edges to your list of possible choices, and then you do that over again until you've visited every single node in the graph. So it's not too complicated, but then you can just kind of see this playing through here, that it just kind of shows how this works kind of visually. Because as they say, a picture is worth 1,000 words, or maybe, I don't know, 500 lines of code. But so that's basically how Prim's algorithm works. So now the main thing we need to do is, okay, how do we assign a cost to our edges? So we've got all those beautiful purple lines that I drew. So how can we actually take those and put a weight or cost to them? So first what I did is I was like, hey, let's just use the distance between those nodes. That's probably, we'll see what that gets us. So if we take and figure that in, things are starting to look pretty good, right? So we took that crazy purple mess I had, and now I've got this less of a mess here. So obviously just taking the distance between all these nodes to connect those together. Great. Problem solved. Let's deploy this out. We're good. Move on to the next project. Then designer sends in this picture and they go, hey, I ran your thing, and for some reason it's running a jumper across the floor to connect these two things together. That's not good. So we got a little bit of a problem. Because obviously just using the distance between these nodes is not going to work out. We need to think about, okay, we got to actually worry about how this electrical routes through your products, because it's going to make a difference, because you'll have weird things like this happening if you don't. So what we can do is we can increase the detail that we have on our graph. We can add in some points that how you actually get from point A to point B, instead of just saying, go from point A to point B. Because as you know, if you open Google Maps, it doesn't ever tell you the directions it gives you. It doesn't just give you the direction as the crows fly. You actually got to like follow the roads to be able to drive. So what we ended up doing was we kind of found the points of interest within our product that the electrical components would route through. So like the certain places on the edge of the panel, things like that, that would be where the power would actually route through. So if we take a look at that here, I've added these circles. These brown circles to show, okay, we have on the edge of each panel, there's a place that the power can exit and to go into the next panel. And then inside of the frame, we've got, these points here that the power can traverse from the bottom up. I've kind of simplified this from how it actually works, just because the complexity doesn't matter here. But then we can see if we connect all of these together, how the power would actually route through there. You can start to see, okay, how the power might actually get from one of these nodes down here all the way up there. Then the tricky part is how do we do that? Because when you look at that, it's an easy thing to think about, but then to write code to actually make that happen, it's a lot more of a complicated problem. So now we need to introduce a pathfinding algorithm to actually make this happen. So we, again, we talked about the problem, blue circles, blah, blah. Okay, basically everything I just said. So one of the algorithms that I found to be the most useful is called the A-star pathfinding algorithm. So let's not worry about really too much about what it does here. I've got some images I'll show that'll kind of walk through this. But basically kind of the terminology I want to talk about is there's an open and closed list. So the open list has your possible options of where you can go next. Your closed list has a list of all the places you've been. Then there's some terminology that goes with this algorithm. There's G, H, and F. So G is the cost, how to get from where you started to where you are currently in the graph. H represents your guess from where you are to get where you need to be. So if I'm here now and I need to walk over to the next conference room and say, okay, that's 100 feet. You're just taking a guess. And then F is just simply the combination of G plus H. It basically tells you what the cost of, if you were to go there, what's that total cost at that point to help you make a decision if you want to go to that node or a different node. So I've got my friend here, the pathfinding cat. So basically think of this as kind of like a simple tile-based game. And so you can't move into the hash areas. You can only move a single square at a time. And then it needs to have, there's going to be a square that'll have a bone in it that the cat's trying to get to. So what the cat's going to do is he's going to look at all the possible options of where he can go. So he can go to any of these green nodes. And then the different numbers represent the, so the top left is the H value. The bottom is the current G value. And then this is this is the H value, the G value, and then the F value in the top corner of each square. So then you can see what the cat does is it's always going to take the choice that all the choices it has, it's always going to take the one with the smallest F value, which basically says that's the cheapest way to get to that point. So obviously with this first choice, he's going to move right one square into this square over here. And then as soon as he gets into this square, now we've got two more possible options that can happen, is he can move up or you can move down. So then again, given that the cheapest F value is the square below him, he's going to keep moving that way. And then as you get down here, you add a single more option. And then at this point, you actually have an interesting choice here, because you've got actually all of these have the same F value. So in this case, he's kind of a magic cat, so he kind of knows where he's going. So he's just going to luckily pick the square that helps him get there. But in reality, it doesn't matter. If you were to pick one of these other squares, eventually these are going to increase, the other squares that we could add here would have an F value that's too high. So it would not choose to go that way. It eventually will end up here as your choice. So then again, we keep adding squares. And again, we've got another one that's F value of 7. And just kind of keeps going here. As you can see, as he gets here, and then he gets over a little bit further. And at this point, you're at a spot where, okay, your end location is actually now inside of your open list. So then that means you're basically almost done. So then you obviously would want to choose that as your next choice. And then once you're there, you basically just take the path that you took, reverse it, and then you know how to get from point A to point B now. There's a couple interesting things that can happen sometimes. Sometimes, in this case, this doesn't show up, but there may be some cases where you may get to a node that you've already been to, or a node you know how to get to, but you haven't been there yet. You get there a different way. And so sometimes when you do that, you've got to worry about updating the value if it's basically a better path to get where you wanted to go. So now we'll look at this kind of walkthrough of the logic here now in words. But basically, how this works is you add your starting point to the open list. From your open list, you add all those options. So basically the cat, we added all the squares that were next to him as his choices. And then we pick the square with the lowest F value that we haven't been to yet. And then we remove that node from the open list, put it in the closed list, because now we have visited that node. And then for all of those nodes that the new node is connected to, we drop those into the open list. The main thing is here now, with adding new nodes, we want to make sure if it's closed or we've already been there, we don't worry about it. If it's not in the open list, we put it in there. And then this kind of special case here, and I kind of outlined this because this kind of bit me in the butt for a while, is a hard bug to find because I didn't handle this case properly to begin with when we implemented this, and that sometimes I'd get some weird pathfinding going on because sometimes it would just literally depend on how, like some of my loops, what came out first. Sometimes it would do weird things. Other times it would do what I'd expect. So that's kind of why I'm just kind of hammering this one home a little bit, that if you end up at a node that you already have in your open list, you just need to check and see if how you got there that time is cheaper than how you got there before. So you want to swap those basically around and use that path basically. So you update where you came from to use that instead. So another fun problem I had was calculating my H value, because originally what I did was I just used the distance. So I just did, me.distance to the target, using just regular, 3D point. I found that this actually caused some weird problems at certain places, because when you'd have like a 90-degree bend in the panels, depending on how those yellow nodes were set up, you would get it would start to pick some different paths to go. And just to kind of show this home here, I've got just like simple, triangle math here to show that we're trying to get from S to E. So then you can see here that as I got closer to, if you think of these as two separate panels in our run, we would have, as you get closer to this bend, when you calculate the F value, you actually see that it would calculate the F value for this situation versus this situation differently. So then it might potentially start taking some paths that are not your best path to take. So it's just kind of want to drive home the point of making sure you think about how you're implementing your H value. So when I had this problem, I had to go ahead and take a new way to calculate the H value, and then I basically swapped to using, instead of just the distance from point A to point B, is calculating a Manhattan distance instead. And you can think of that as like driving a cab in New York. You can't just plow through the buildings to get where you want to go. You got to stay on the road. So by doing this, originally we have the green value, which is like, hey, just do the distance between A and B. So when we swap this over to using the Manhattan distance, there's a couple different things that can happen here, but essentially what I ended up doing was just taking the vector between A and B and then just summing the components of that vector. So summing the X, Y, and Z values to give me a better indication of how far I was away from actually my endpoint. And again, that was many days to figure out, oh, hey, my H value calculation was wrong. After I've got this whole thing built, and just these weird situations that things would act slightly different. So now we've got a pathfinding algorithm. We got to create a minimum spanning tree. So now we can finally connect these things probably about how they might actually look inside of the product, going from connecting these two harnesses together. So it's looking good. So now we got to figure out what the heck parts we actually have to push to the bill of materials to actually make this happen, right? Because it's great that they can hook together, but they need to know how they hook together to be able to order the parts, or it's not really useful to our designers. The tricky part about this is this is very product dependent, obviously, how this works. So this is where I said, using your deep knowledge of how the product works, you can make some good decisions about how to do this. So there's not a lot I can, I can tell you, I'm going to tell you kind of how we did it, but again, it's your product can make this be very different in how this works. And a couple of the products that I put electrical into for us, the most complicated part has been figuring the parts at this point. It's like all this algorithm stuff is like cake next to figuring out what the parts need to be. So really, there's always going to be special cases too that you're going to have to worry about. Because sometimes pathfinding makes sense, but that's not actually how your designers spec or install the product. So you're always going to have to handle some special cases. And so what we ended up doing for some special cases, such as like some in-feed types, some product intersections, maybe dependent on part cost, is those don't necessarily follow, oh, this is the shortest distance from point A to point B, so this is what we should do. So we basically kind of built a simple decision-making engine that would just say, okay, we've got these options. Is this an in-feed? Is this a certain type of in-feed that has a special case? Okay, yes, we're going to use that route instead of this pathfinding route instead to decide what to do. Because it's just easier to do that than try to, you got a pathfinding algorithm, works great, let it do what it's good at, and then you handle special cases on a case-by-case basis, really. Because if you're going to try to hit this, swing at this with one hammer and try to every time and just use that one hammer, it's going to make your life hell. So. And then lastly, I just kind of want to talk about some of the issues we faced, because these kind of were the most difficult things for us to come across and find solutions for, and just kind of so you can be aware of them. The first one that was probably the most difficult was in the end, so we had the graph, everything was great, but then again, I'm going to come back to my little part here, is our power harnesses that go in our panels have this little guy attached to them. So this can go in the panel this way, or this way to connect to the next panel. And so that presented some problems because you wouldn't know which way this needs to go until you start hooking everything together. So we had to deal with that kind of after the fact as things were being hooked together, having to keep track of the orientation of where this kind of tail or whip is going. And so that was an interesting problem that we had. I don't know if everybody has electrical parts that look like this. I know some people have parts that are similar to this, some people don't. Whereas if we would have just had, kind of without this and just had, you just would put a jumper or something between these, you wouldn't have to deal with that at all. And another problem we had too was that each of these actually on some sides, you can see this actually has two different plugs on this side. So you can actually have two different parts plug into one of these. Or if the power was flowing the other direction, you could actually feed power out to two and actually three things because there's one on this other side as well. So some parts have that many plugs. And then we have another part, such as this one, that only can connect up to three things. So it's got the two on this side and then only the one on this side. And so that created a lot of fun problems with us on the orientation, as well as just terminology when talking with people, because our training team would refer to some parts or orientations of those parts one way, and then I would call them something else. And then an hour later in the meeting and arguing, we realized we're both saying the same thing, even though we were arguing about it. So again, just the product knowledge is important and figuring out how to deal with these things. In the case of this, we basically took, okay, after we've selected, put a new path into our graph, we then basically would go through and recalculate the direction of all of those whips and parts to make sure that they're, were accurate and available. The other fun problem we had to deal with was debugging, because I like to explain this to our designers when they come in and like, oh, well, I routed the power and it did this weird thing. And I basically told them is that I basically coded a 4-year-old. You tell this thing not to do certain things when you're routing the power. You say, hey, only these parts are allowed and, to connect. You can't connect these two things by going through the base of the panel. So it says, okay. but the code really wants to connect them together because that's what you told it to do. So instead of going through the base of the panel, it's going to maybe jump the power all the way up to the top of the panel, come across and back down, because like, hey, you said I couldn't go through the base of the panel, but why can't I go up? So you start to see these weird things. And besides just knowing, having your intimate knowledge of how all this is coded, it's still very difficult to debug what it's doing sometimes. And so one of the things that I built that helped me debugging is I actually, when it's doing all the routing and traversing the graph with the A-star algorithm, is that it's basically every edge that it picks to go, I would push to a list, and then I could run an animation that I could then grab that list later, and I could sit there and just like click the animation, and every click I could see it would add a new edge, so I could see exactly how it was trying to traverse across the graph. And then I did some other stuff with a lot of like just displaying text in the 3D world, just so I could see what was what, because sometimes you're spitting out objects to your console, and it's like, oh, that's power harness 54 ID, and it's like, okay, well, I don't know what the hell power harness 54 ID is in space, so just taking that and then just transposing that on space so I can see what's connecting to what and things like that, because it is a very tricky thing to debug, and it even is for me now when we get problems. And it just, as time goes on, the problems get more complicated, because usually it's something smaller and smaller each time that's just not quite right, or even then it's just maybe it's a case that we need to handle specifically. So then the next thing is looking at automation versus design intent, because we wanted to automate as much as we could for the designer, but we needed to make sure that we don't kill their design intent by automating too much. And again, an example is with this part that we have here, is this part goes a specific way in the panel. So if you wanted to have like the outlet on the left of the panel, it goes this way, whereas this tail kind of goes through the entire length of the panel. But if you wanted the outlet on the other side, this part has to be positioned this way. And so sometimes the designers don't necessarily understand those rules very well about our panel system. And so when they would try to route sometimes, then you'd end up with a situation where these are in neighboring panels of each other, but they have no way to connect to each other. So then we basically decided at that point, we just kind of show an error to the designer saying, hey, you need to move a part, because we don't want to decide for them, oh, well, we could just flip that part to the other side of the panel, but maybe there's a reason they put that there. So maybe they need to make a decision about forcing a specific part in there and things like that. So that was always an interesting discussion all the time with work, and that was working a lot with our design team to find out, what do we want to do here. The other thing was customization for the designers, because some things we want to automate, but then we found out that there was a few things that sometimes they wanted to do, because they would want to control, maybe instead of putting some like of the jumpers and stuff to be on module with the panel, meaning that if you have a situation where you're spanning, maybe they've got 4 panels that are 36 inches wide, and you only have outlets in the 2 extreme end panels, we would need to put like a jumper part or something like that or like an extension cable to connect those two. And so we'd have the option where they could say, the cheapest option would be, okay, we'd put our longest cable between those two, it's just a single cable, but then that potentially kills their reconfigurability. So we give them the option, like a customization option. They say, okay, well, you can check this box, and then instead of putting in one long cable, it'll put in like 2 36-inch cables inside of each of those panels. So that way, in the future, they can reconfigure. And we've got a couple other options like that, but that's probably the easiest to explain without you guys understanding our product that well. And another thing that we kind of struggled with a long time was how to visualize this for the user, so they would know easily what they're looking at when they see the power routed, what parts there are, because people need to obviously audit the drawings and things like that. And so how can we make it easier for them to be able to audit what the parts that it's dropping in there? Obviously, they could look at the bill of materials and do the complicated work, look at part tagging, things like that. But how can we make that easier for them? And so that was, and I still don't know if we have the greatest solution for that. It's kind of an ongoing thing. And then it also comes with installation viewing, because some products it's simple, but if you have products that can, like that, if you remember that picture of the panel where we've got power stacked on top of each other, you think of your install drawings, a lot of times, usually they're using like a 2D file. Well, how in the heck do we communicate that there is, 4 of these things stacked on top of each other in the panel, and then the ones that are stacked, so they might be might be a different type of that product than the one that's below it. So how do we, pass that information on? And again, that's something we don't necessarily have the greatest answer for, but we've worked with our designers to say maybe you should start putting that kind of that transparent 3D view where we show things are connected. Start putting that in as part of the installation process, installation drawings, or using like an elevation view of the electrical, so they kind of see, hey, this is how this connected together, rather than us trying to come up with some complicated way to show that on a 2D view. Um, and then again, just the detailed product electrical knowledge where I talked about, it was hard to find people that had the answers about this in our product, just to know how these things hook together, how they work, how they're routed. It was always very difficult. I don't know if, I'm sure you guys have probably all faced that problem with some product or another when you're implementing. It's just finding the right people to be able to talk to and have kind of an open line that you can ask questions to. So, but yeah, that's all I got. Anybody questions, concerns?
So this whole the idea of applying A-star to generate a while back, but I couldn't resolve a good way to do that, since A-star is all about I want to go from A to B. I don't care how I get there. I just want to do the best.
Mm-hmm.
So generating a spanning tree off of that was just going the algorithm a bunch of times.
Yeah.
I didn't know what note to start from.
Yeah. So in actuality, what I did there, and I kind of glossed over, well, I didn't talk about it, but so what I actually did was I actually had, how we do it is I actually have two separate graphs. So I have, let's see here if I can go back to that slide. It'd be fun to work my mouse from over here. So, so I have, so from this drawing out here, I would create basically a graph like this in code that would just say connect these things to each other. And then I actually figure out how to do the pathfinding as an entirely separate graph. And then so then I use this to calculate the minimum spanning tree, whereas I would use my pathfinding algorithm on the other graph to decide what the cost is of those edges. So then I would take to get from from here to here, I would use the A-star algorithm to decide the cost of that edge.
So if hypothetically there weren't any additional nodes to what you're seeing here, the A-star would be meaningless. Because all the cost is pretty much just business.
No. So I use the A-star to calculate it. So the A-star would actually, I'd have the separate graph. So if you think about that graph with the brown, where's that at? So then I have this graph also. Yeah, if you didn't have that detail, yeah.
So you're using the A-star just to evaluate this into the.
Yeah, so I'm just using the A-star, so I say, okay, how do I get from point A to point B? And so then I have the path and then the cost. Then I save that with the edge on the graph that I use for the minimum spanning tree, essentially. So at least one person understood what I was talking about, so that's good.
Not really a question. It sounds like you have already been composed a lot of work. To me, it seems like you probably need to go into like what we call nowadays the data science kind of subject, I would say, because the estimates and the animation, all of those, you probably need those if you really need to go fully animation.
Mm-hmm.
Yeah, looking to data science is probably something that.
There's one way to see it. We can say that we just came up with this yesterday. We can say we use Google technology, right? Because it's like it's A-star and all that kind of stuff. Is that what part of the map?
And then as far as calculating, we talk about how you figure the parts to get from point A to point B. There goes the cat again. So like what I ended up doing for at least one of for our panel systems is, since I knew how the parts worked or what parts came in what, and then I basically actually analyzed the path that this thing took to decide the parts that I would use. Since like in this case, I know if these are 36-inch panels, then I'd have a 36-inch line segment in my path that came back from the pathfinding algorithm, and I could see that that path was flat. So then I would know nowhere else in my graph do I have lines that are 36 inches long. Most of the segments were much shorter than that. So I know if I had a perfectly level line going, if the X or if the Z value was the same on that line, then I always know that and it's greater than, like whatever our smallest is, 24 inches. Then I know, okay, that's got to be going through an entire panel, so I would know what part to pick, essentially, in a nutshell. But
if I may interject, one thing that I think makes sense to say, I don't know how far you guys
not everybody has auto routing their extensions, but there's some with, right? And as far as we know, the hard part, at least for us in the beginning, was okay. What do we need to know to solve the problem? So we didn't even know what we didn't know.
Mm-hmm.
So I guess we talked a bit with CJ because I think he implemented a couple things for other extensions, and then we figured out okay, there's the minimum spanning tree. Oh, so now we have a lead.
Mm-hmm.
So I guess that one interesting thing about Tyler socket is like okay, solving this kind of problem, keep the math material as a reference, and then at least you know what to look for. Because I mean, for us, it wasn't obvious.
Mm-hmm.
We weren't
Yeah.
graphs and too much computer science.
Yeah, it's kind of like, if walking up, you have no any idea about carpentry, and I say, hey, build me a house, and you wouldn't even know where to begin necessarily. What tools, materials you need. So this at least kind of gives you the tools and materials that you might need to solve that problem for your products. I'm sorry.
When did you write this? Like
So you would have been what, end of about a year and a half ago?
December of 17.
Yeah.
Like, not totally sure on this, but I think there's a lot of stuff coming into more recent companies. Like I've seen, I looked at it for like an abstract electrical, and I think
Mm-hmm.
the components stuff that was talked about earlier today has been used in the system. So
Yeah.
I'm just curious if you utilize any of that.
Mm-hmm.
It sounds like pretty much
Nope.
everything in the system
Well,
was homegrown.
yeah, and it comes back to, I don't remember who brought up the point about us just not knowing what's necessarily out there. Like in one of the previous talks, like a lot of times as external developers, we don't always know what's out there and what it can be used for. Like I even know, like it seems like a lot of the dev conference topics sometimes repeats, like, oh hey, here's vessels, here's how vessels are used, and still people aren't quite, it's not clicking sometimes, if you will, with kind of some of our external developers, it seems like. But so we kind of just took the problem as like a lower level programming problem and solved it that way. But I think some of the same ideas could still, a lot of these same ideas will probably apply no matter how you look at tackling your electrical problem. So.
Another thing we use graphs. I don't know if you guys rely on those, but for example, we have walls, and we have to calculate the amount of trims that go into every wall and the corners and what kind of pieces you need. So graphs were also used for that, to calculate the cost of and what kind of part you need, the size, in a simpler way, but still it's a good tool
Mm-hmm.
to have, I guess, right?
Yeah.
So, with what I saw there, it seems complicated and time consuming to do that.
Oh yeah.
So, I guess how important is getting the shortest path? If you're saving 12 inches of jumper, I guess it seems like I would generally favor a solution that's going to be like we just go from left to right, connect them, we go up and down, connect them, and if we have a little bit extra than normal, I guess the users can fix that themselves.
So,
and see a better way.
Mm-hmm.
Otherwise, it just seems like
so
much time and complication for
oh yeah,
6 inches of jumper.
and
That's
yeah, yeah, and yeah. So the actually thing is, with our panel systems, we only use jumpers to go up and down, and I want to say that we only have in the product catalog that you can order with panels, we only have like 2 lengths of those, and that's it. Don't quote me on that, but and so essentially we need to know again how are we getting from here to here, and then so with that, what parts we need to order, because I think like in this case we'd have the harness here, we'd have a pass through, and then we'd have a jumper hooked onto that to go up basically. Yeah. And again, it depends on your product, right? I know I've done some of the electricals for some of our products that it's much simpler and we don't really care about that. And so then we don't go into this much detail to solve the problem.
Matter how complicated your wall is, that instead of every time you go to the corner or something, necessary have 4 joints or not, or 2 joints or not. But if you have whatever he has come there, you just go direct. Just let's say you put in one of the outlet or step somewhere in one corner and do the feed on the other corner, you automatic by when. I think that's what I see. And the application actually very like it's mentioned earlier, there's from college
Yeah.
If we have the time, I go for it.
Yeah.
I think I agree.
Mhm.
For
Yeah.
us panel, we have complicated, and I found that this if we have the time
Mhm.
to implement this, I see a lot of more benefit for the users.
Yeah. And we get the design, like our designers are very used to specing this all manually, and coming from, especially because we just transitioned onto CET like a year and a half ago or something like that. So our designers are very used to, at least the ones that knew how to spec electrical, they knew exactly what they needed. And so if you were off, I grant in this case we didn't have the jumper problem, but there's been some other products where we've done that, and it's like, oh no, that should be a 13-inch jumper, not a 12. And so we get a lot of that feedback from them as well. And so it's a battle with some of those things to say, does it really matter? I mean, as long as it'll connect, does it matter? But so, any other questions? All right.
What's the algorithm for putting together
The minimum span tree? Yeah, that was Prim's algorithm. Yeah. And as I was like trying to find solutions for a lot of this stuff, it was like I'd suddenly be like, oh yeah, to solve this problem, use Prim's algorithm. I'm like, oh yeah, I remember the name of that from college. I don't remember how to use it, but yeah. So, or if you guys see me around, if you got questions later too, feel free to ask questions too. I don't know if my answers will be helpful, but I can at least try. So, all right.